So in this question, we are trying to prepare the following compounds from suitable starting materials, and the starting materials should not exceed 6 carbons each. Okay, so first of all, I'm going to skip D because D is a little too complicated for us to do. There's just too many steps, so I'm just going to skip D. But we'll do A, B, C, and E. Okay, so let's start with A. And maybe a good idea out here is to add a page. I'm going to add a page, and we'll just do A on this page, and if we need another page, we'll do another page. Okay, so there we have A. Okay, so now as you can see, we have an ether, and you're trying to build it from a 6 or less starting materials, which means at some point in time we need to start our reaction with benzene. Okay, our reaction sequence with benzene. So let's think retro. If we go backwards from this, what's going to happen? So a good strategy always to go backwards is to always try to cleave or try to break the bond which is forming the ether. So it could either be this end or this end. And now if you have to make a decision, you want to always break the end that is not connected to the 3-degree carbon, or the 4-degree carbon in this case. Okay, and the reason for that is because this piece will become the alcohol and it'll make your life a lot easier. So let's go ahead and do that. So when we cleave this, we're going to make this piece the alkyl halide. So there's going to be a bromine popping off here, and then this piece becomes the OH. Okay, and OH. Okay, so we're going to let that piece be and try to figure out how do we make this from benzene. So let's go ahead and start the synthesis. Okay, so there's your benzene. We're going to add a carbon first. Best way to do that, to add just a single carbon, is to use the Gattermann Koch formulation. Carbon monoxide HCl, AlCl3, CuCl. And that is going to give you C double bond OH. Then we're just going to reduce the C double bond O. We can use the Clemenson's ZnHg HCl. And that is going to give you, let's write that properly. And that is going to give you CH3. Then we can use NBS, CCl4 with H nu. And that puts a bromine at the benzylic position. Now we kind of, as you can see, we made this piece. Now we just bring this piece in, but before we bring that in, we're thinking Williamson's ether synthesis. So let's start from here. We add a base like NaH. That's going to deprotonate the OH. And then this is going to react with this. And essentially that bond goes there. Sorry, the electrons attack this carbon and kick out the bromine. And that basically ends up with giving us the product that we want. There you have it. All right, let's take a look at B. How do we make B? So B is actually a relatively simple molecule to make. And again, if you just count 1, 2, 3, 4, 5, 6, so there are already 6 carbons. So all we're really doing is trying to figure out how to make this ether. So we could just think retro, similar strategy as we did before. We'll break the bond out here, and that is going to give us, put a bromine out there and put an OH out there. And now the synthesis would simply be, if you take, I'll change the color out here. If you take this molecule, we add NaH, pulls off the hydrogen, and then this piece just attacks this, goes there, and guess what we get? The product. Pretty straightforward. All right, let's take a look at C. So in C again out here, the more branched piece can have the OH, the less branch will not have the OH. So we'll cleave from here. Again, I'm thinking retro. So that's going to give me a BR out there. And then you have an OH out here. As you can see, that's 6 carbons. That's actually 7 carbons. So we need to figure out how to make this. But I just showed you how to make this in this synthesis out here. As you can see, you start from here, you go down this pathway, and there you have it, right? So we follow the same strategy to make this piece. So we know how to make this piece out here. So all we got to do is connect them together. So what we'll do is we'll add NaH to this piece. And then this piece will attack this, goes there, and guess what? It gives you the product. All right. We said we'll skip D, so let's take a look at E. So really, we need to be focusing on this piece. Again, same strategy out here. We can always disconnect from here out here. And then as you can see, that piece becomes the OH. There's one problem though, and you'll realize the problem pretty quick once I do the retro. And the problem is basically means that we won't be able to do this in the same way that we've been doing the others. We have to do something a little different. So if I cleave that, that piece becomes, the bromine shows up here, and then the other piece is an OH. And now the problem is that if I did a Williamson's and grabbed the H off this, then the next step in the Williamson's is a negative on the oxygen, which should attack this. But you can't do that on a benzene ring. And actually, in this case, you could, but it's just not the best strategy because you already have 3 electron withdrawing groups, so you could do it very easily. But if there were no NO2s out there, then you'd run into problems. So I'm going to show you a different way to do this, assuming you didn't have NO2s out here, okay? If you did have the NO2s, you could still use that way, okay? So the way to do this is to think of that the precursor to this piece was an epoxide, okay? So that means something attacked, there was an epoxide out here like this, and if this piece became a Grignard, and that could have attacked the epoxide, okay, making the OH out there. So that's the strategy we'll use. So we'll make that into a Grignard reagent, Mg dry ether. NO2, 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 Mg, Br, and then we react that with, oops, let's move that, this epoxide, okay? What that basically does is it basically goes here and kicks that off. And the second step, when you hydrolyze it, that actually ends up giving you the product, which is this piece, okay?